Hello, everyone. I hope you're all healthy and well. Welcome to the next talk in our Golden Webinars in Astrophysics series. Today's speaker is Sheperd Doeleman, who is an astrophysicist at the Harvard-Smithsonian Center for Astrophysics and founding director of the Event Horizon Telescope project. My name is Thomas Puzia, and together with Elisabeth Artur de la Villamois, we have organized today's webinar for you. We have again arranged for simultaneous language interpretation, which is provided by Mr. Patricio González, who is already simultaneously translating for us into Spanish. En sus dispositivos pueden escuchar la interpretación al español de la conferencia al pinchar el botón Interpretación que se encuentra en la parte inferior derecha de la aplicación Zoom y seleccionar Español. We would like to acknowledge the generous support for this series from the Center for Astrophysics and Related Technologies, also known as CATA, for its Spanish acronym.
Thank you so much for all your feedback and comments. If you're watching a recording of this talk on YouTube, please leave your comments below. If you would like to support the Golden Webinar series or give us feedback, please send us an email. If you have any questions during the talk, please type them in the Q&A window. You can also upvote questions and comments on them. We will select the best questions for the discussion after the talk. The link to the live version of this video will be automatically taken down by YouTube shortly after the streaming ends. However, the final high-resolution version, both in English and Spanish, will be uploaded in our channel in the next few weeks. So before we begin, I would like to briefly introduce our other panel members that are with us today. Of course, Sheperd Doeleman as our speaker, Patricio González as our interpreter, Thomas Puzia and myself as co-hosts. From the faculty at the Institute of Astrophysics at PUC, we have Ezequiel Treyster and Franz Bauer. From the Institute of Astrophysics at PUC, we have our postdocs, Paula Ronco and Demetra De Chico.
Let's introduce now our guest panelists that are with us today. So we have the great pleasure of welcoming Rohan Radko-Onkar, who is a research intern at Gemini Observatory. Itziar de Gregorio Monsalvo, who is the head of the Office for Science at the European Southern Observatory in Chile. Luigi Foschini, who is a researcher at the National Institute of Astrophysics, INAF, at the Brera Astronomical Observatory. Neil Nagar, who is a professor of astronomy and astrophysics at the University of Concepcion in Chile. Vladimir Garas, who is the head of the Relativistic Astrophysics program and professor of astrophysics at the Astronomical Institute of the Czech Academy of Sciences in Prague. Barry Barish, who's the professor of physics at Caltech and at the University of California at Riverside, and the 2017 Physics Nobel Prize laureate. Julio Navarro, the Lansdowne Professor of Science at the University of Victoria in Canada. John Blakesley, head of observatory science staff at NSF's NOR Lab. Paul Heunigen-Hühne, professor of philosophy at the Institute of Philosophy at the Leibniz University of Hanover in Germany, and lecturer at the Department of Economics at the University of Zurich. And last but not least, we have our great Q&A manager, Ricardo Acevedo, who will be sifting through the comments and questions and selecting the best for us today. So now it is our great pleasure to introduce Sheperd Doeleman as our Golden Webinar speaker today. Shep got his bachelor degree at Reed College, Portland in 1986, and then spent a year in Antarctica working on multiple space science experiments at McMurdo Station near the Ross Ice Shelf. He then earned his PhD in astrophysics at MIT in 1995. After visiting the Max Planck Institute for Radio Astronomy in Bonn, Germany, as a recipient of the DAD fellowship, Shep came back to MIT in 1995 for a postdoctoral fellowship and later became an assistant director at the MIT Haystack Observatory. He's currently a senior research fellow at the Harvard-Smithsonian Center for Astrophysics and a senior general engineer at the Smithsonian Astrophysical Observatory, a project co-leader of the Black Hole Initiative and the founding director of the Event Horizon Telescope project. Shep and the EHT collaboration received now many awards, such as the National Science Foundation Diamond Achievement Award in 2019 and the Breakthrough Prize in Fundamental Physics last year. This year, Shep has also received the Henry Draper Medal from the US National Academies of Sciences. in 2019, he was named one of Times Magazine's 100 most influential people.
Shep has focused on problems in astrophysics that requires ultra-high resolving power, the ability to observe fine details of cosmic objects. His research employs the technique of very long baseline interferometry, in which widely separated radio dishes are combined to form an Earth-sized virtual telescope. Shep and his group at MIT pioneered the instrumentation that enables VLBI to achieve the greatest resolving power possible for the surface of Earth. And he carried out the first global experiment using these new systems that successfully measured the size of the supermassive black hole at the center of the Milky Way galaxy and in the galaxy M87. His group at the CFA and the Harvard University Black Hole Initiative works on simulation and instrumentation for the EHT effort in the development of simulation softwares for refining the telescope array and imaging, and for the expansion of the Event Horizon Telescope to enhance its overall capabilities. So we now hand it over to Shep, who will tell us about the Event Horizon Telescope from first images of black holes to real-time video. So please, Shep, whenever you want.
Okay, thank you very much. Let me, is that coming through okay?
Yes.
Perfect, okay. Well, thank you very much for that gracious introduction. I can tell you that while Time Magazine may think I'm very influential, at home, I'm just another person here sheltering during this pandemic. But thank you very much. It's a real pleasure to be here, and thank you to the organizers for inviting me. I'm going to speak to you today about the Event Horizon Telescope, walk you through some of the underpinnings. We'll start slow, talk about black holes, and we'll move to imaging black holes. And by the time we're done, I hope to make the case that we're not as far off as we think from making real-time video of black holes. And that would let us test Einstein's theory of general relativity, his theory of gravity in novel new ways, and give us as close a look as we are ever going to get at the event horizon. I'll talk about results that are on behalf of the entire EHT collaboration, and I'll even go beyond that. I'm happy to acknowledge a lot of the funding sources that we have for this visionary work, which is at the bottom here. So I want to start off a little bit unconventionally. I want to show the first X-ray of the human hand by William Röntgen. This is a picture of his wife Bertha's hand. These were times when you could have a high vacuum, high voltage system in your basement and invite your spouse down and ask them to lay their hand on something and zap away at it, and they would do it. But this is remarkable. This was the first time we saw something that was hidden from our gaze, the skeleton of a living human being, and you can see her wedding ring in this picture. Another picture I'll show to motivate what we're going to talk about today is this fleet. In 1665, Robert Hooke looked through a microscope and saw a hidden world, a fantastical world, but a hidden world that was wonderful to study, and it opened up entirely new areas of science. And with black holes, I want to convince you that we are taking some of the first pictures that are like these pictures, terrifying, but also gateways to a new understanding. So I want to show you first an optical image. And what you're looking at here is the smudge in the center is the galaxy Hercules A. It's about 2 billion light years away. But if you look at it in the radio, you see something that is hidden. You see jets of emission streaking out from the center of this galaxy that stretch for 1.5 million light years. The only thing we know of that can power this kind of activity in the universe is accretion of matter, matter falling onto a supermassive black hole that liberates that energy. And because the black hole is spinning, it ejects these jets from the north and south pole. And here's kind of a cartoon of what that looks like. Magnetic field lines that are swept in by the gas drawn to the black hole twist, and they centrifugally speed charged particles out as though they were beads trapped on a wire that is spiraling around. And you get these light speed jets streaking away from it. The total energy in these lobes is equivalent to 3 billion supernovae, 3 billion stars exploding. So black holes liberate huge amounts of energy. They are terrifyingly efficient engines in the night sky. And we want to zoom in all the way to see one for the first time. That is what the premise of the Event Horizon Telescope was. So let's start off a little bit, 100 years ago to speak about gravity. Of course, the person on the left is Einstein, and he reconceptualized our notion of action at a distance that Newton had given us as to the underpinnings of gravity. He said mass deforms space-time, and then the deformed space-time tells matter how to move around it. But one of the predictions of Einstein was that light would be deflected by gravity. And you see that in the lower right here, that if we were on Earth and we were looking at a star that just grazed the path by the sun, we would see a deviation in the star's apparent position because the light ray is deviated by gravity as it comes to Earth. This angle was about 1.7 arc seconds, or 1/2000th of a degree. It seemed at the time that that would be very, very difficult, almost insurmountable to measure. And yet it was measured. In 1919, 2 expeditions left England, one to Principe off the coast of Africa, one to Sobral in Brazil, and they photographed the positions of stars during a solar eclipse. And they're shown here with these horizontal bars. You can't really see the stars in there. And the stars had deviated exactly by the amount predicted by Einstein. And this is a picture of the New York Times Magazine from November 10th, 1919. And you can see this famous headline, "Lights all askew in the heavens." Men of science more or less agog over results of eclipse observations. So this was the first time that our concept of gravity had changed, and that we were seeing the bending of light around an object like this. So not long after the theory of general relativity was finalized in 1915, Schwarzschild solved at the front lines of World War I, by the way, the Einstein's field equations, and he showed there was a radius if you compacted mass into a single point where light could not escape. This is called the Schwarzschild radius, and this is the point of no return. This is what defines a black hole, this point where the escape velocity from that object is greater than the speed of light. So for many years, these were mathematical curiosities. Nobody really thought that they could exist in nature, that nature would forbid something like this from forming. Yet, astronomers began to see curious things in the sky that hinted that objects that were incredibly dense did exist in the night sky. So on the left, you see a white dwarf. This is what happens when a star, not unlike our sun, goes through its whole evolutionary cycle and it collapses. It is the size of the Earth, and it has a density of about 10 to the 6 or a million grams per centimeter cubed. A neutron star is the death cinder of an even larger star, but it compacts down now to the size of Boston, the city where I live, and it has a density of 10 to the 14 grams per centimeter cubed, but still able to sustain itself by quantum pressure. And then you have a black hole, and that results because at some point you try to collapse a large enough star at the end state of its evolution that nothing, not the material in a white dwarf, not the neutronium of a neutron star, but nothing can prevent the complete collapse onto a singularity, a point of infinite density. Now, how do we see black holes? Why do black holes shine? This is a mystery that is really interesting to think about. If you drop an apple that weighs 100 grams onto the Earth, you will release about a joule of energy. Now, this is enough for you to power your cell phone for about a second. Okay, but if you condense the Earth into a marble about an inch across or a few centimeters across so that it is a black hole, same mass as the Earth, and now you drop the apple, it keeps accelerating, and it achieves a velocity very close to the speed of light before it impacts that black hole. It falls all the way to the center of the Earth because there's no surface, and it liberates 10 to the 16 joules. That's a 1 with 16 zeros after it. That's enough to power all of Manhattan. Not for a second, but for an entire year. So this is the power of gravity. It's the same mass object, but when you configure it differently, when you reduce it down to the size of a black hole, you can liberate massive quantities of energy. And that's the secret to why black holes shine and why they drive the complex dynamical processes we see in the night sky. Now let's get to black holes. When you think about a black hole, you might think that this is what one looks like, and Kip Thorne and a number of very gifted computer graphics professionals made this for the movie Interstellar, and they got a lot of stuff right. They really did get many things right about this, this particular kind of black hole in which all of the material orbiting around it is confined to a sheet in the equatorial plane. So it's though a pancake is orbiting around it. And of course, this was first seen by Jean-Pierre Luminet in 1979. He wrote a wonderful paper in which he showed how the bottom part of the disk, where emission is leaving that area, is lensed up, so you see it in the right-hand photographic plate, and the top, it also gets bent, and you wind up seeing exactly the same kind of morphology that we see in the interstellar frame. And this hole here is called the black hole shadow. Now, Jean-Pierre Luminet was not satisfied just with making that cartoon. He also made computer simulations, and you see one here. This thin line here is the photon orbit. This is the point at which light is forced to orbit in circles around the black hole. So this is a unique thing that only happens for black holes. And he even made the first animation. So in 1979, this is incredible, he made the first animation of what light around a black hole would look like. Really a visionary. Now, if you want to understand what a black hole would look like on the sky, you can go back even further. And Max van Laue, exactly 100 years ago, drew this diagram, and he asked himself, what would the size of the shadow of a black hole be? And he knew instinctively that it was very much related to the Schwarzschild radius, because that's the radius at which when light goes through it, it can't return. So that has to be the source of the shadow. But what defines the shadow was the photon orbit. This is the point where light can orbit the black hole. And when he fired imaginary light rays back from the Earth to this black hole, he realized that these paths that just bordered on this circular orbit, those were the ones that determined what was in the shadow and what was outside of the shadow. Interior to that, you would see a dark spot. Outside of that, you would see light. And it turns out that the diameter of that shadow was the square root of 27 times the Schwarzschild radius, or the square root of 27 times a handful of constants: Newton's gravitational constant, the mass of the black hole, the speed of light squared. This is remarkable. If we could measure the size of this shadow, we could lay a ruler across space-time, and using this equation, measure the mass of the black hole and verify that Einstein's theory of gravity was right. Now, it turns out that modern applications of computers and the modern simulations that we run all show this basic feature. So whether you are looking at a schematic model on the left, a high-performance computing simulation in the middle, or a general relativistic magnetohydrodynamic simulation, I know that's quite an acronym salad, on the right, you see this circular feature, which is determined by that photon orbit. And always you see a bright part on one side, and that's because close to a black hole, everything circularizes. So there's always a part of the flow that's coming towards you at near light speed, and that's Doppler boosted. So just as a train whistle becomes higher in pitch when it's coming towards you, light, when it's coming towards you, when it's emitted by relativistic plasma, appears brighter. So in all of these, you will always see one side that's brighter than the other. What's important about this is that no matter how you light up the space-time, the metric, the geometry of the space-time determines what you see. So you always see this circular feature, you always see these Doppler boosted bright patches. Now, the best opportunity we have to see one of these objects is in our own Milky Way galaxy. Here, let me go back there. So this is an optical picture of the Milky Way galaxy. If you go deeper and you take a radio image, you'll see infalling streamers of gas coming into this bright spot, which we think marks the center where there's a 4 million solar mass black hole. And of course, the Nobel Prize was won last year by the team, Andrea Ghez and Reinhard Genzel, for their amazing work tracing stellar orbits around an unseen mass at the center of the Milky Way galaxy, marked here in the star. It is beyond doubt now that there is a supermassive black hole there that weighs 4 million times what our sun does. And one of the objects that we hope to observe with the Event Horizon Telescope is this source, our own black hole in our own backyard. Now, the other object that we can look at with the Event Horizon Telescope and hope to image this shadow feature is M87. And I'm not going to pretend that we didn't do this. We have absolutely done this, and the rest of the talk is going to be about how we did it. But in the upper left here, you see a zoomed out version that shows the supermassive black hole in the center with a jet of high-speed material going off to the right. And we see that because it's coming almost directly towards us. So it's Doppler boosted in our direction. It looks very bright. On the left-hand side, there's also a jet. But since it's moving away from us, it's Doppler deboosted, so we don't see it. But we do see where it runs into the intergalactic medium over here. Now, as we zoom in by a factor of 10,000, we always see this self-similar jet with an unresolved core here, first at 43 gigahertz, and then at 86 gigahertz. What is powering this jet has always been hidden from our view. When you zoom in by a factor of 1 million, and this is made possible by the Event Horizon Telescope, you see this ring of light with an asymmetry just as we suspected. And the size is, as I will explain, completely consistent with the mass we think that the supermassive black hole at the center of this galaxy has. Now, the pandemic has made us feel isolated. The pandemic has made us feel small, lonely sometimes. I don't want to make it any worse than it is, but everyone you know, the whole solar system, and even Voyager 1, which is the farthest person-made object from the Earth, all fits snugly inside this black hole shadow. So there are big things out there, and we are small. But that's also, kind of uplifting in a certain way too. There's a lot to explore in the universe. So, as we want to analyze what we've seen, and I'll go into this in some detail, we can look at state-of-the-art simulations, which you show here on the left. This one done by George Wong, Ben Prather, and Charles Gammy, which show this circular feature, but also these wisps of gas as they spiral around the black hole. So we know what we're after. And if we were to blur this to the resolution that we think we can achieve from the surface of the Earth, we can see this image. And so this is really what we're after, and this is what we specified we'd be able to see with the Event Horizon Telescope. But the question is, can you see through all the hot gas, madly trying to get through the event horizon? Because black holes are great attractors. So the gas that falls onto the black hole, as you've seen with the Apple example, heats up to billions of degrees. And the question is, can you see through all of that hot gas to the event horizon? And in this wonderful simulation on the right here by C.K. Chan and colleagues at the University of Arizona, you see that as you go higher in frequency, as you observe the black hole at shorter and shorter wavelengths, you see all the way to the event horizon. So this is what the black hole looks like at a wavelength of 1 millimeter. And using that wavelength, we can see the details of this event horizon illuminated by the infalling gas. So now we know what wavelength we need to look at. And the question is, can we get the resolution? Now, a conventional telescope simply won't be able to do this. If you took a normal radio telescope, it would only have a resolution that was capable of seeing, let's say, a small coin at the distance of a football pitch. We do something quite different. We employ a technique called very long baseline interferometry, in which we link telescopes on different parts of the Earth. So you see here the concept. We have two different radio telescopes. They're looking at a black hole, and they're sensing the radio waves from this black hole. Okay, each is controlled by an atomic clock. So as we take data, we precisely time tag each of the radio waves as it comes into the telescope. We store them on hard disk drives, the same ones that you would have on your computer. And then we ship them together to a correlator where they're compared. And this then gives us a telescope that in effect is as big as the distance between these radio telescopes on the Earth. So we've turned the Earth into our own telescope. Now, each of these baseline pairs, or each of these telescopes, when paired together, gives us one component of the image that we're trying to make. And by putting many telescopes on the surface of the Earth and letting the Earth rotate, we're able to build up enough data as though we had a full telescope as large as the Earth. Now, on the right here, you can see what we're looking for. The shadow of M87, the shadow of Sagittarius star, the black hole in the center of our Milky Way galaxy, are tens of micro arcseconds. To put that in perspective, we're looking at something that is the size of an orange if we're on the moon, or being able to read the date on a coin in Los Angeles if you were standing in New York City. So this is a completely new kind of technique, a new kind of telescope, and not one that is necessarily very intuitive. So this shows the picture, as I was telling you before, of how we fill in during a night of observation all of the data we need to make the image. So every one of these red lines links to telescopes. Every link is a moving red dot on the right. And after a night of observing, when the Earth rotates, we fill in enough information that we can see and image the source. You can look at these blue lines as being silvered elements of a large mirror. Now, one of the first questions we asked was, is there anything to observe? Is there something towards the galactic center, in the center of our galaxy, where we can really see these kinds of structures? Because if we hadn't seen these structures, we just would have packed up and gone home. I mean, there wouldn't have been any point. If we saw something that was very, very large, for example, we'd know that we would never be able to see through the event horizon. And so what I focused a lot of my career on was developing all the instrumentation that allowed us to do this. And you can see on the left here, we used to use floor to ceiling racks of equipment. It was all analog. We used reel-to-reel tape recorders. And we developed over many years fully digital systems that used banks of hard disk drives that you see here in the bottom right. And we were able to dramatically increase the sensitivity of our telescopes. And in 2008, we carried out an observation where we had 3 telescopes, one in Hawaii, one in California, and one here in Arizona. On the short baseline, the angular resolution of this baseline is such that we would have expected to see all of the energy from Sagittarius star, all of the energy from the black hole in the center of our Milky Way galaxy. But on these long baselines, the resolution was so fine that we should have excluded some of the energy. In other words, if the black hole had a finite size, our fringe spacing or our angular resolution was so fine that we would have excluded some of the energy, and we would have expected to see less energy from the black hole. And that's precisely what we saw here in this graph. On the correlated flux density here, on the Arizona to California baseline is very high. On the Arizona to Hawaii baseline, it's dramatically reduced. This showed us that we were seeing something with a finite size. And when we determined what that size was through fitting, it turned out to be 3.5 Schwarzschild radii. So this is exactly the kind of size we expected to see, 37 microarcseconds, that matched the shadow size. So after we made this discovery, then we knew that we should go ahead and make the entire array, build it out across the surface of the Earth, and make an image. We did the same thing for M87. M87 is a different kind of source. You see here this wonderful image by Craig Walker, made with the very long baseline array at 43 gigahertz. And we zoomed in on the center here, and using the same kind of analysis with the same array, found a source here that was 5.5 Schwarzschild radii across. So all of a sudden we had 2 wonderful targets for the Event Horizon Telescope. Now, I can't stress enough the value of 13-year-old people playing video games, because that's really what drove a lot of the instrumentation that we built. So in order to carry out the measurements that we needed to, with the sensitivity that we required, we needed to record huge amounts of bandwidth. So we wound up we started with very low recording speeds on our VLBI system. We only recorded a little bit of data, but thankfully we used industry standards, industry protocols, and commercial off-the-shelf components. And we were able to match Moore's law, shown here in blue, so that when you plot the recording rate of our systems that we developed for this experiment as a function of year in the diamonds, we match the progress of Moore's law. And we increased the capacity of our systems by 2 orders of magnitude, by a factor of 100, over the course of the development of this project. And what you see on the right is the combined systems that we deployed to all of the sites around the globe. So in 2017, after nearly a decade of focused development, we carried out our observations in 2017 at all of these sites. So we had the IRAM 30 meter in Spain, 2 telescopes in Chile, the ALMA array and APEX at the Atacama site, the LMT in Mexico, the SMT in Arizona, the submillimeter array and JCMT in Hawaii, and of course the South Pole joined us at where else? The South Pole. We had wonderful weather. I'm not sure if we were lucky or what, but we had good weather the whole time. We had 10-day window and we triggered 5 days and everything worked. So all the preparation, all the instrumental development, all the triple checking, it all paid off. And I want to point out that for Chile, Chile brought the key enabling site. The ALMA site at the Atacama Desert, in a single stroke, increases the sensitivity of the Event Horizon Telescope by a factor of 10. And it really was the key. And we spent about 6 or 7 years just working on making all of these telescopes in the array operate as one single telescope, so they could join the EHT as a single very powerful element. And that was an effort all by itself, and a number of people, you can see here all these different logos, all helped to do that. Now, I talked about bringing the data all to a central correlator facility, and when I say bring the data, I really mean bring the data. So people pack up disk drives, and this is Andrew Nadolski, one of the technicians at the South Pole, and he's packing up all the drives. They're flown to Christchurch, New Zealand, and then on to Port Hueneme in California, and then on to the correlator at Haystack Observatory. And they show up in a FedEx truck, just like everything else we order these days. We unload the disk with a forklift. We open them up, and then we warm them up because they've been cooled during their long voyage. And they're put into a big library. And each of these represents our precious data that were recorded on site, and that are then compared with data taken at exactly the same nanosecond at other geographically spaced stations. So let's talk about the data. I remember where I was when I first started seeing these data. I was at a dinner, and some postdoctoral fellows came and showed me this. So this is the same kind of plot that I showed you before. You have energy on the y-axis and the baseline length on the x-axis. So these are short baselines over here, long baselines over here. And you can see this characteristic bounce that comes back up and then bounces again. And having looked at these kinds of data for many years, I knew immediately what we were looking at, as did everybody else at the dinner. So you can't fit this with a single blob. This is a Gaussian blob, and a blob like this would not thread through all these data points. You can kind of start to fit it with a disk, but even there, this second null, this second bounce, is not in the right spot. If you start modeling it with a ring, now you can trace some of the major features here. And it is when you have a crescent with a little bit of brightening on one side that you immediately see, just with your eye, that you are seeing something that's very ring-like. And this is when we got extremely excited. but excitement does not really translate into hard physical evidence. So we created new imaging algorithms to tackle this from first principles. And you can see on the left all the papers written by members of our group to tailor radio interferometric imaging processes for the Event Horizon Telescope case. So we minimize this term here, just to get a little bit technical. This first term is to fit to the data, to make sure that we are fitting all of our models to the data. And the right here is a regularizer to ensure that we are looking at a smooth distribution, that we're not looking at something that is too crinkly on the sky, or God forbid, that goes negative on the sky. So this ensures positivity. And what I'm showing here is the moment by moment step through this process with the data that I showed you to create an image. And you'll see that annealing point there where we kick the process to see if we're really at the proper minimum. And then we settle in to this ring feature. These are algorithms that were tailored just for the Event Horizon Telescope. There's another algorithm that I'm showing you here, which is based on a more traditional imaging technique. And we had different teams that were using different techniques to image this source. And so the first technique I showed you was teams 1 and 2, and this clean technique, which is a much more traditional algorithm, was used by teams 3 and 4. So we had different methods that were in tension with each other. And that was by design, working to make these images. The teams we put together were amazing. We split up into 4 geographically separated teams, all working with different algorithms. And the reason we split up into 4 different teams was not only to get different looks at the object, but also to prevent groupthink. And what I mean by that is that it is very difficult to tell the difference between fried chicken and labradoodles. And if you think you are trying to find a labradoodle, it could be that you're actually looking at fried chicken, and a group that's small enough can convince themselves they're looking at something that they're not. So, and if you think that this is bad, try telling the difference between, chihuahuas and blueberry muffins. So we wanted to avoid the kind of groupthink that could infect a group of people that are trying to image something that they have never seen before. Thankfully, this really paid off. And we all came together in July 24th in 2018 in the sub-basement of a building at Harvard called the Black Hole Initiative. And each team unveiled their first images. The first 2 teams used that regularized maximum likelihood method that I showed you first. The teams 3 and 4 used the clean algorithm, and they were all seeing the same kind of structure. And this is when we knew that we had something that was truly amazing. Now, we really focused on ways to convince ourselves and our peers that we were seeing this ring. So we did look at a different source. This is a quasar, or the center of a completely different galaxy, where we see this core and a jet morphology that I talked about before. And here, where we don't have the resolution to see the ring, we see the core in the upper left and the jet, just as we would expect. And all of our different imaging algorithms showed the same thing. So this gave us great confidence. So when we don't expect to see a ring, we don't see a ring. So we haven't made algorithms that see rings everywhere, because as the saying goes, to a child with a hammer, everything looks like a nail. So we don't want to always find something that we're looking for. In addition, we had independent data on 4 separate days. And you can see here on each day, the image that we reproduced and the baseline sampling on the bottom here. So each independent data set we had all converged on the same image. So we were doubly convinced that this was a robust result. Now, how important are these sites? As with real estate, as they say, it's location, location, location. That's what matters. So if you only had 2 sites, let's say the LMT here in Mexico and the Arizona site, you would only be able to tell how big an astronomical source was. And you can see here in the middle where the data are in the Earth-sized aperture. If you added the almacite, for example, well, now you can see smaller objects, but you can't see the morphology. You can't see the ring structure. If you start getting outriggers here in Hawaii and you use all those data, you can begin to see the hint of this ring. But it's only when you have the full array, when you have baselines that stretch from Spain all the way to Hawaii, that you get the resolution and the full coverage enough to use the algorithms that we developed to find this ring. And as we think about the next generation instrument, which I'll finish with at the end of my talk, we will discuss where to put those telescopes to make the best images. So how do we measure the mass of a black hole? Well, I showed you before on the right, we have the square root of 27, and that's essentially multiplied by the mass of the black hole divided by the distance to the black hole. And that gives us the angular shadow diameter, which is what we're trying to measure. So on the left, you'll see an image, and we trace around and find the ridge line of this image, the brightest part of that image. And you can see on the right that we wind up seeing a histogram of radii, and we can read off not just the diameter, but also the uncertainty in the size of this ring. And we should be able to read off directly then the mass divided by the distance. Now there is a complication. The complication is that we want to find this photon orbit. It's that photon orbit that is the square root of 27 times the Schwarzschild radius. And I'm showing that here with the white dashed line. Now, if we translate that to the image we observe, we realize that that is smaller than the ring we actually measure. And the reason for that is that there's a lot of emission outside of that ring. And that biases the fit to this ring that we make in the black to be larger than the actual photon orbit. So the question is, how do we deal with this? Well, we make the assumption that the angular shadow diameter that we're measuring, the black dashed ring here, is proportional. It's equal to alpha times theta sub g, or the angular gravitational radius, which is related to the mass divided by the distance. And we tackled this in a very interesting way. We used hundreds of simulations of what a black hole might look like. We ran it through a system that created synthetic data sets. We created data sets as though we had observed that simulation with the Event Horizon telescope. And then we imaged those fake data sets. Now we had images where we knew exactly what the size of the photon orbit was. So we could say clearly what the comparison was, what this alpha parameter was. And we did this over and over and over again, and we found the average bias, the average difference between this black circle and the white dash circle. And the average was about 11.5 in numerical terms, with a 10% uncertainty. So doing this, we were able to find the constant proportionality, but we incurred a 10% uncertainty penalty. Now, what does that mean? Well, we were able to get very, very consistent values of theta sub g, or this gravitational radius, over many days with many different techniques. And since we know through really the work of one of our panelists, Professor Blakesley, the distance to this galaxy, we were able to read off the mass. So the mass was 6.5 billion solar masses. This is remarkable. So we've taken a ruler, laid it across space-time. We've used the distance to this black hole to measure its mass. And we've done it in an entirely new way using Einstein's theory of relativity. Now, it turns out that it matches other ways of measuring the mass of this black hole. So there's a group led by Carl Gebhardt that uses the motions of stars around the supermassive black hole, and he and his team get the same mass that we do. So there's another way of getting the mass that matches ours. This gives us even more confidence that our techniques are quite valid and robust. So where are we? Before we go on to think about next steps, let's see where we are. The black hole shadow has been detected. The results that we have are consistent with all expectations from the simulations we've done and from the theory of general relativity. The asymmetry we see here on the bottom is due to lensing and that Doppler boosting that I described before. And we even can talk about the direction of the spin axis. So if you take your thumb and you point it slightly into the page and down, and your fingers curl up under the black hole, where the image is the brightest, your thumb is pointing in the direction of the spin of the black hole. So for the first time, we've been able to tell which way the spin of the black hole is pointing for a supermassive black hole. And GR, because the mass that we measured matches the mass that the other people have measured for M87, we verified GR at around the 17% level. And that's because, again, the mass from the shadow that we derive matches the stellar dispersion masses that other people have gotten using different techniques. But again, the calibration technique that we used, the fact that we needed to use all those simulations to tell what that constant proportionality was, sets a limit of 10%. Even if we knew everything perfectly, this technique would still only let us get to within 10% of testing general relativity. Now, can we do better? And I think that we can. And I'm very excited about the next steps because I think that we can make percent or so measurements of GR. So what I'm showing you here on the left are light rays being bent around a supermassive black hole. And the n equals 0 ring, these are light rays that are bent just subtly around the black hole. So think of the hot plasma bending slightly around the black hole. But photons that make a full U-turn around the black hole, they light up a much more narrow ring. This ring that we call the n equals 1 ring, all part of the same emission, is much more closely tied to the general relativity of the situation, much more tied to the geometry of space-time. Now, let me zoom in here. So here's the full simulation on the left. And here you see the n equals 0 ring, which is all of this tufty emission that is very, very thick. The n equals 1 emission is extremely narrow here, much more tied to the geometry. And the n equals 2 ring is only maybe 1 micro arc second or less across. So the full image actually consists of nested rings of concentric lensed photon orbits that get closer and closer to the true photon orbit. Now, can the Event Horizon Telescope in a future configuration detect that? And I think that we can. So on the right here, you see the same kind of diagram I've been showing you a couple of times, where you see the energy versus the baseline length. And you can see here that in the future, the EHT will be sensitive to this green region. And there are a number of dips you see here. And these all correspond to the n equals 1 ring. So I think that we will be able to, in the future, measure that n equals 1 ring. And we won't have to use this simulation calibration that I talked to you about before. And we'll be able to get to a percent or so matched to general relativity. Now, the reason I'm optimistic is because we've already run some simulations. This is work by Avery Broderick, Dom Pesci, and others. They've taken multiple simulations that you see here on the top, and they have fitted them with synthetic data, with fake data sets, as though we had observed it with the Event Horizon Telescope. And they have fit a ring, and then they have, in a hybrid sense, imaged all the tufty emission around it. So we assume there's a ring, we fit for it, and then we image the remainder. And in each case, we can extract with great accuracy the photon orbit. Now, this hasn't been proven yet with a real instrument, but we are tailoring a new extension of the EHT now that will be able to do this. So through new instrumentation, new sites, and new algorithms, we hope to extract this n equals 1 ring and get a much better test of GR. So the remainder of my talk is all going to be about the next generation instrument and how we're going to build that out. So all the blue points you see here are the Event Horizon Telescope as it exists today. And all the red points are potential sites. These are high altitude sites where we may be able to build new dishes and add them to the array. And this is some work being done by Alex Raymond and a team of people at SAO and internationally. And they have done just some phenomenal work surveying all of these sites. And you'll see that many of them, of course, lie here on the Andes Mountains in Chile. So Chile is going to figure quite prominently in what I'm going to discuss next. Now, the concept, the idea here is that because we have such large sensitive dishes in the Event Horizon Telescope, we have ALMA, for example. We have the NOEMA array in France. We have the Large Millimeter Telescope in Mexico. These are so big that we can now think about using small dishes, maybe only 6 to 10 meter diameter dishes. And what you see here on the right is that the sensitivity of a baseline to a very strong site allows us to use a 6 meter dish or so and meet our technical specifications. So this star shows us our target performance. And when we link a 6 meter dish to, let's say, the new Large Millimeter Telescope in Mexico, which is the orange line, we exceed our expectations, we exceed our requirements. So we can start thinking about adding 10 modest-sized dishes to the Event Horizon Telescope array, filling out the entire Earth-sized telescope to give us unparalleled imaging fidelity. We'll increase the bandwidth for more sensitivity, so we'll increase the rate at which we record data. We will record at higher frequencies or shorter wavelengths to increase our angular resolution. And we'll design this over the next couple of years and then build it out before the end of the decade. So everything I'm going to show you after this is what we hope to do in the coming decade. Now, one of the questions is, where do we put these dishes? And I'm not going to go into great detail on this, but we have multiple different tests that we run to find out the suitability of all of our new sites. So when we ask ourselves, is this new telescope location good? We ask, well, how well does it fill in the UV plane? How well does it fill in that Earth-sized aperture after a night of observing? And that's shown up here on the right. We also ask ourselves, after a nighttime of observing, what is the biggest gap in our coverage? What is the biggest hole in our Earth-sized mirror? And then we also ask, when we run a full simulation and we try to image one of our shadows with this new telescope, how closely do we recover the known image? So running these 3 tests, we wind up creating the best possible locations on the surface of the Earth for the new dishes. Now, so I'm going to show you some results that we get here. Now, on the left, what I want to show you is in gray here and in black, these are all the sites represented in this aperture plane of the sites that we can field in 2021. This is what we'll be doing this year. But with the next generation EHT, adding 13 new sites on the Earth, we recover also all the blue, the dark blue and the light blue positions here. And you can see that we get almost everything. We nearly fill the Earth-sized aperture. So one of the questions we ask is, how does the black hole that we observe right now link to the large jet that we know exists in M87? And on the right, you see the input simulation that we used here with the black hole powering this large-scale jet. And what I'm going to show you is the iterative process for imaging this with this new array. And you can see that the algorithm locks onto not just the black hole at the center, but also the low surface brightness jet launching region. So you're seeing for the first time, if we could do this for real, if we could do this with actual data, how a black hole is powering this jet. Because at the moment, we don't have this low surface brightness capability. We can't tell you how the black hole relates to the jet. Now, for humans, dynamical input is extremely important. So if we were to observe this source, if we were to observe M87 every 3.5 days with this next generation array, we would wind up seeing a movie. So on the left, you see the input simulation created in a supercomputer. And on the right, what we think is eminently possible, very feasible with the next generation telescope. This would be the first black hole cinema that we have available to us. And it is understanding the dynamics of how the black hole not just feeds this jet, but how it is dynamically coupled to it, which would unlock the secret of how black holes power some of the most energetic phenomena in the night sky. Now for Sagittarius A star, which is the black hole again at the center of our Milky Way galaxy, the mass is much smaller, so the dynamical time scale, the time over which it changes, is extremely short. Matter, when it orbits M87, can take 3 days, or perhaps even 3 weeks to move around the black hole. But for Sagittarius A star, matter can make a full orbit in half an hour. So during the course of an observing night, Sagittarius A star changes its appearance while we're watching it. So while we're trying to build up our Earth-sized aperture, it's changing its appearance. It's a little bit like taking the lens cap off your camera while somebody's running by. You get a blurred image. But when you build in enough new dishes, you have enough snapshot coverage that you can recover the full movie. So on the left, again, you'll see a simulation. Well, I'll just blur that simulation in the middle. And then on the right, you'll see the reconstruction moment to moment based on the aperture coverage you see here in the inset. So even in the blurred image, you can see that there's a rotation. But with the reconstruction, you also see a rotation. And this is just the first time we've ever attempted to do this. So over the course of the next few years, we'll be refining the algorithms and really be able to tell what the flow is around the black hole. And this will then show us the periods of matter orbits around a black hole, not just the bending of light. And that will be an entirely new test of Einstein's theory of general relativity. So just as one implication of this, we asked Avery, Broderick, and the collaborators here at the Smithsonian, could we use these techniques? Could we use the next generation array to see objects that were farther away? And so they simulated the M87 black hole, not at 17 megaparsecs, which is where it actually is, but at 50 megaparsecs. We put it 3 times farther away. And this is the truth image here. There's a ring, and you see in contours the whole jet as it's moving away. And by using this hybrid method that I was telling you about before, fitting the ring and then imaging the resulting large-scale emission, they recovered it with very high fidelity. So what we think we can do now is extend the search space, the volume in which the Event Horizon Telescope can image and tell the size of these rings of lensed light around supermassive black holes. And because the accessible volume grows as the cube of the angular resolution that we can get, we may be able to increase the volume by a factor of 30 to 1,000. So instead of having 2 sources, we may have 10, even more sources for the next generation telescope. So I'm coming to the end here, but I want to emphasize that this is really a huge collaboration, and we could not have done this without a number of dedicated scientists around the globe. As with all projects, it started small. In the beginning, there really were only like 10 of us running around to the tops of mountains and trying to make these first measurements. But to build out the full array, we really required a number of people, and bringing these people together, forming the collaboration, and most importantly, keeping them together. That was really a trick, and we had to play that trick over the course of a full decade. But it's really been a wonderful joy to work with this entire team. Now, I'll wind up, but before I do, I want to say that there is some possibility that we can go into space. You could increase, this is a whole new topic, but we could use orbiting satellites very close to the surface of the Earth here to fill in the UV plane on a time scale of hours and make movies that way. And we can also think about putting a telescope extremely far away from Earth, getting unparalleled angular resolution. And this would bring tens of thousands of black holes into range. So in addition to the next generation telescope, there's also the space expansion, which is a completely different direction, complementary to what we can do here on the Earth, but also very, very exciting. And these are the kind of movies that we could make going into space. So the next generation EHT will give us a very good look at the dynamics, but going to space would give us about a factor of 5 increase in angular resolution. And this is all possible maybe not for me, but our children will be seeing black holes in incredible detail. So as I wind up, I want to give you a couple of thoughts about the larger implications of this. When we had our press conference in April of 2019, the most surprising thing was coming down in the morning from our hotel rooms and seeing this image on the front cover of every major newspaper around the world. And then we knew there was a truly human dimension to what we were doing. And I think one of the reasons it resonated was because people saw an intractable problem, a seemingly impossible problem, successfully tackled by a worldwide collaboration of people that worked across borders, that simply pooled their resources to do something that was visionary. And I think that is something that can be grafted not just for other scientific projects, but also is a template for working on some of the larger issues we face. And we also got a nice global doodle. And then for those of you who follow the television show Jeopardy, this was one of the questions that was asked in a recent episode of Jeopardy. And I think we all know what the answer to this question is. We do feel that about 1 to 4 billion people saw this image, so it's also a teaching moment. You know, how can we tell people about science broadly? So the organizational lessons that I personally have learned on this is that what kept us together was we had a focused science vision and goal. I like to talk about a 100-year handshake with Einstein, and in that way it's very similar to the LIGO project, really going back to our roots, making fundamental measurements. We did always act as though people like Einstein and Schwarzschild were looking over our shoulders, and when that happens, you really want to get it right. We managed our expectations all throughout the project. We had continual victories, first just detections of horizon scale structure, detection of magnetic fields. We were able to show the funding agencies how at every step of the way, we were making real scientific progress. We grew this international team from an early high risk, small band of ruffians to a follow-on moderate risk and much larger team. And that was required. It's the natural evolution for a project like this. We met technical challenges by harnessing Moore's law and linking our development of cutting edge instrumentation to commercial off-the-shelf commodity electronics. And we identified key enabling sites like ALMA in Chile and the LMT in Mexico, and we invested heavily in them to increase our sensitivity. Now, believe me, there were a lot of politics involved, as with any great venture, but we did accrete new partners that brought in considerable resources from Europe. They brought in 15 million euros at a very important time. We used large international facilities that already existed, and with the use of new instrumentation, we made them do something that no one of them could have done themselves. And we kept, unfortunately, there were some institutional interests that crept in, but we always kept our eyes on the science. We took calculated risks. Some people say we jumped off cliffs and invented parachutes on the way down. Well, not really. We also were very, very careful in our development of technology, and we required precursor results to go forward. We assembled a fantastic team, and to all you early career researchers out there, this was a project where young people played leadership roles, and that was really important to motivate everyone. We also used what I like to call creative tension. There wasn't one technique to image the black hole. There were 4 teams, each in tension with each other. But when we wrote the papers, the results from each team were showcased in the paper. So there was not a down select. Nobody felt as though their work was going to be excluded from the final result. And in that way, we created a camaraderie and a teamwork that paid off in the end. Some things did not go smoothly. There was one of the original 6 papers where there was real intellectual combat. People really were disagreeing about the right way to go. But thankfully, we had a deep bench of experts that were able to come in and adjudicate some of these disputes. And so that's really what I wanted to say. And the last thing I'm going to point out is that when I get into taxi cabs right after this result, and I asked the taxi driver whether they knew about this result, they said, oh, yes, And I said, well, do you believe it? And they said, oh, yes, these scientists, they really know what they're talking about. And I read up on this and I know what's going on. It's not always the case. So you're seeing a nice graph here, and maybe people know what this is. But if you showed this to somebody, you would say, wow, over many, many years, there's something very definite happening, and it's unquestionable. And then you realize you're looking at CO2 on the summit of Mauna Kea, of Mauna Loa. This is the underpinnings of global climate change. But this is very controversial. So how can people believe of the black hole result in their bones, but then have a hard time understanding climate change? This is what we as scientists need to grapple with. How can we educate everyone? How can we get our message across? How can we take the lessons of the scientific method and discuss it with everyone and come to some conclusions about how we can tackle large problems? And last, I can't resist, in addition to the flea, in addition to the skeleton, in addition to this black hole image, LIGO has also opened up this amazing window for us. And I like to think that all these four things, Röntgen's wife's hand, the flea, LIGO, and the Event Horizon Telescope image are all part of the same thing. This view for the first time of gravitational waves is also quite singular. And in each of these cases, we saw something invisible. We saw something that was hidden from our view, and that is extremely compelling. So I just want to leave you with this image. It has been incredibly inspiring for us. The next generation EHT is going to take it even further. And I hope it also inspires you. Thank you very much.
Thank you very much. This is an absolutely amazing achievement and a fantastic demonstration of how technology, theoretical and experimental astrophysics development go hand in hand and produce this beautiful symphony of insight and knowledge. Absolutely remarkable. Thank you for this. We're going to take a 120-second break for everyone to go through the questions and submit also their questions, for our interpreter to relax a little bit, and for Shep as well. And then we're going to come back after the music. So please look through the Q&A window and submit your questions now. All right. So we have plenty of feedback and a great Q&A queue. I will start with the first question, which is going to go off in a little bit vanguard tangent here, taking advantage that we have Barry Barish with us also, and ask you, what about how is the response, let's say, time scale of in the future pointing the next generation Event Horizon Telescope at something that appears to be in spiraling and merging as of, imaging these candidates that LIGO is going to probably produce in the future, the last movie that you have shown, or the last animation that you have shown in your presentation, and actually making a real high definition RGB movie out of this?
Wow. Well, I'll do part of that, maybe, and Barry will likely want to chime in. So the size scales of the black holes we're looking at with the EHT are vastly different than the ones that LIGO sees. So LIGO is looking at stellar mass black holes, maybe tens the mass of our sun, and we're looking at black holes that are billions of times what our sun weighs. At the same time, we may be able to, with the EHT, look for binary black holes at the centers of galaxies. So there's a galaxy called OJ287, for example, where we think there are two supermassive black holes orbiting each other. And so we would be able to see those, but those would never coalesce in our lifetime or anywhere near it. But there are future gravitational wave instruments like LISA, which is going to orbit the sun, where we start to look at the same kinds of objects, and that would be quite interesting.
Yeah, let me add. Your answer is exactly what I would say. We're very different masses, but in order to understand the binary systems better, it's going to be a combination of the space experiment, because it measures much earlier the black holes when they're further apart and lower frequency, and then they'll scan the same black hole merger can then be predicted and seen on the Earth in whatever instrument LIGO is become at that time. So R isn't exactly a movie, but maybe a long history of the merger, which gives us a different way to test general relativity and really the origin of these black holes, which is the other big puzzle.
I'm very excited by that, by the way, but the potential of these two totally different techniques possibly meeting in the middle somewhere. That's it's kind of interesting to think about.
How would an extremely long baseline addition, I wonder if Elon Musk has contacted you already, putting something on Mars. Of course, there is this degeneracy of, duty cycle of the gas, timescale, monitoring, right? And then how you sample the UV plane on what timescales. So they are sort of in conflict with each other. But I can imagine that, a 500 million kilometer telescope would inform many things, right?
Well, that's a great question. So if we were to put a telescope at the second Lagrange point, which is a special orbit away from the Earth and the Sun, which is stable, then we would have a baseline length of millions of kilometers. And the nice thing about that is that the interferometer, the telescope formed by the Earth with that far off satellite, is exquisitely sensitive to the finest scales. So we could look at the photon orbit that I was telling you about on very, very small scales. And even though we can't image, we could model. So it starts to become a little bit more like the LIGO situation. And if we could do that, then we could measure tens of thousands of black holes. In fact, we can look at black holes all the way to the edge of the universe. And then we could do a demographic study of black holes across cosmic time. So there are real advantages to going out that far. Also some challenges. I'm not sure if a Tesla is going to get all the way out there.
Fantastic. Okay, let's go to Luigi next.
Thank you for your excellent seminar. It is very interesting, and congratulations for your excellent result. I would like to ask you about Sagittarius star. I understand that you are still working on data, but do you have some preliminary estimate of the mass, just to know if it is consistent with the estimate of made by Genzel and Guess with the stellar motion?
Yeah. So it's a very good question. First, I can't say anything about it because people in the collaboration would kill me. That's the first thing. We are working very hard on that. The key here is that the reason it's difficult is because of the time scales. So Sagittarius A star changes every half an hour. And so the same data that we have for M87, where we can look at an object that is not changing during an evening, becomes much more complicated for Sagittarius A star, where it's in motion. So we really need to start to take into account that dynamical change. And we have developed some techniques to do that. And I'm very optimistic that we will come with Sagittarius A star results soon, maybe even this year. I would hope they would be this year.
Thank you.
Let's go to John next.
Okay, Shep, thanks. You gave a really good explanation of how you convert the size, the angular size of that shadow to use that to derive the Schwarzschild radius, and then the mass based on first the work of Max von Laue and then the simulations you talked about. And so using that information and the distance, you can get the mass. So I have kind of two questions from really a popular level perspective, because I know there are a lot of high school students and non-science people in the attendee list. So the first one is, so you gave the distance in megaparsecs. If you convert that to light years, it's something like 55 million light years. And this is a question that I was asked at a public library when I showed your beautiful image. And they said, okay, well, so it's 55 million years ago. How do you actually know it's still there? And so I gave kind of an astronomer answer, and I would be interested like how you would answer that that question. It's could be either really hard or really easy, depending how you approach it. And my second question is just, you mentioned a lot about the UV plane and kind of the lobes and things, but you never really said what the heck is the UV plane. And is there kind of like a popular level explanation of that? Because, I mean, unless you've had college physics, you may not know that.
Yeah, so let me tackle the first one, which is how do we know that M87 is still there, or what does it look like now? I suppose that one of the ways I think about it is that telescopes are time machines. So you look out into the universe and you look at distant objects and you're seeing all the light that came to us from a long time ago. And you see objects that are close to us and we see them at more recent times in their evolution, just because you see more recent versions of them. And so astronomers do population statistics, and they understand the populations of things like stars or galaxies by looking at different distances. And for M87, we know what kind of galaxy it is, and we see different types of that galaxy at different distances. And we can say something about its evolution, and that kind of galaxy is going to stick around for timescales much longer than 55 million years. I mean, 55 million years for that kind of galaxy is like a day for us in our whole lifetime, or even less. So you could ask yourself, I saw my friend yesterday. Do I think he looks basically the same as he does today? And the answer is, well, yes. I mean, he might have gotten a haircut, but he's going to look pretty much the way he did yesterday. So on a time scale that galaxies operate in, we can be pretty sure that M87 has not changed its appearance too much. The second question you asked on the UV plane, it is a difficult concept. When you take two telescopes far apart from each other, they're measuring just one component of the brightness. It's as though you break a picture down into multiple little pieces, and each telescope pair is sensitive to one of those pieces. All by itself, one telescope pair can't really reproduce the image. But if you put enough of those together, if you sweep out enough of the points in that aperture plane that I was showing you, or as you call it, the UV plane, if you were to sweep out all of that UV plane, you would be able to perfectly reconstruct the image. So we sweep out enough of that plane that we can use algorithms to make that image. So what I would say is that each telescope's pair is picking out one piece of the image.
Thank you.
Of course, for those who know Fourier analysis, it's one Fourier component of the image. So.
Okay, let's go to Etienne next.
Thank you. So first of all, thank you very much for this nice talk. I have plenty of questions regarding the future of this project, and you answered plenty of these questions. But I have a latest one. In your opinion, what will be the most difficult part to make this future next generation EXT project successful? Could it be related to the technical side, or more in the coordination of this large international group? Or could it be more related to politics, funding? So basically, what is needed to make this project successful in the future, especially if you are thinking on putting an antenna into space?
Yeah, so it's a great question, and you see, I have scars all over my body from the politics and the fundraising and so forth. So I think that from the technical point of view, everything is in hand. It really is. We're putting known dishes in new locations, but they're known. We are building out the electronics, but again, we're using commercial commodity electronics to do it. There will be some algorithmic development, but I'm very optimistic about that. Really, it will come down to organizing the team, taking the Event Horizon Telescope and scaling it up by nearly a factor of 10, forming the international collaborations that are required for that, and building new sites and fundraising. So I really think it will wind up being more of a political and fundraising exercise. I mean, of course, doing the hard work there's a lot of work to be done, but some of the major challenges will be in those areas. Although I think that once people realize that we're looking for executive producers for the first black hole movie, I hope they will sign on.
Okay, thank you very much.
I'm sure there are many candidates for this. So let's go to Ezequiel next.
Yes, well, hi, thank you very much for the wonderful talk, and of course, congratulations on this amazing result and what's coming in the future. My question is about measuring black hole spins. I had the feeling from reading the first series of M87 papers that actually constraining black hole spins is difficult with this technique, right? So I was wondering about what are the prospects for getting better constraints on M87 and extending it, I guess, on the next generation EHT to other black holes where we can measure black hole spins.
Yeah, it's a great question. So the first thing to understand, and I didn't cover completely in the talk, is that the black hole shadow, its size is relatively insensitive to spin. So if you have a Schwarzschild black hole with no spin, it will be the square root of 27 times the Schwarzschild radius across, about 5.2. If you have a black hole that's spinning maximally, a Kerr black hole, maximal spin, then it's about 9/2. So it's about 10% different. And the reason is that even though the light orbits are constricting, the lensing or the magnification of that orbit as it moves around the black hole, as it's lensed around the black hole, compensates for that. So you wind up seeing roughly the same size. So even so, the spin of the black hole introduces some asymmetry. The shadow winds up flattening on one side. So if we can image the n=1 ring that I described, we would begin to see that much more pronounced than we can right now with the EHT. So I think there is possibility to do that. But more probable is that we will time the orbits of matter around the black hole. We will see a magnetic reconnection event in the accretion flow. It will light up, and we will see that orbit the black hole. And the orbital period of matter as it circulates around the black hole, that is exquisitely sensitive to spin. So in other words, at the innermost stable circular orbit, for a maximally spinning black hole of the mass of Sagittarius A star, the period is 4 minutes. But if it's a Schwarzschild black hole, it's half an hour. So it's a full order of magnitude difference. So that's how I think we will first make our measurements of spin, by looking at the motions of matter.
Little aspect related to this. So far, you're observing in one frequency. Would a color inform this aspect a little bit more?
Oh, yeah, it's a wonderful question. As a matter of fact, some of the results I showed, I didn't go into this, they mix two frequencies together. And it turns out that currently we're observing at 230 gigahertz. That's just the frequency of the radio waves we're receiving. And we want to increase that to 345 gigahertz. And in doing so, we increase the angular resolution, but we also increase the coverage and all the elements of the image that we're sensitive to answer John's question. So we actually fill in our Earth-sized aperture by looking at that extra frequency and make much better images. And that's important because many things around the black hole are wavelength dependent. The gas looks different at one frequency than it does at another frequency. But one thing that doesn't change is gravity. Gravity lenses all wavelengths of light the same. It's what we call achromatic. So if we can fit the ring with this new frequency, 345, that same size also has to fit the data at 230 gigahertz. So we have a very powerful discriminant on the strong gravity features versus the messy astrophysics that can change with frequency.
And nature throws you a calibration source right in the sky, right? It's the photon ring, right?
We hope.
Yeah. Okay, let's go to Elizabeth next.
Yes.
She will take a few questions from the Q&A.
So there is a question from Pablo Garcia, and he's asking if you were to choose between having the largest baselines possible on Earth with as much atmosphere, or having somehow a shorter baselines on the moon without atmosphere, what would you pick?
Oh, so I assume what he's at, first of all, wonderful question. I assume you're saying, would you want an array on the moon with no atmosphere that's smaller than an array on Earth with an atmosphere, I would choose the array on the Earth, because we know now how to tackle the atmosphere. We have found a way around the atmosphere on the Earth. But I would turn it around, and I would say, maybe the question that one could ask is, would you rather have an antenna on the moon or build out more antennas on the Earth? And that's a more complicated question, because having an antenna on the moon would give us access to completely different range of black holes. So if I had to choose there, I'd have to think about that one.
Okay, so in the meantime, while we search, because they're jumping around, let's go to Vladimir next.
Thank you very much. It is, I think it is very amazing to see how this ingenious calculation of lumina, which you showed at the beginning, reproduces in what you see with EHT now. But you know, intensity or brightness or even color is not everything which we have in photons. It's not entire information. There is also polarimetric information hidden in that. So I wonder if you can comment on prospects for polarimetry, because we know that astronomical objects are often polarized and radio astronomers observe with polarimetry resolution.
That's a great question, and as Neil, who's on the call, knows very well, we are actively working on this. Our goal is to come with the same image of M87 that we have now, but showing the orientation of the magnetic field overlaid on top of that. Because of course we know that this supermassive black hole launches a jet, and we know that that jet launching process is tied to the magnetic fields that thread the event horizon of the black hole. So understanding the magnetic field configuration will be the first step towards understanding how energy is extracted from a spinning black hole to launch that jet. And what I can tell you is that results are coming in the not too distant future on exactly this. So you are 100% right. We've recorded all the polarization information, and we're using that to learn something about the plasma around the black hole, the jet launching mechanism, and how accretion feeds the black hole.
Yeah, that's really great. Thank you very much.
So there is a question here from Vicente Villagra, who is asking about the importance of the Chilean sites, and you mentioned them already in your talk, but could you elaborate on, you know, how much more power we can get out of similar sites, let's say in Chile? You showed the candidate sites compared to ALMA.
Yeah, so right now we use the San Pedro de Atacama site, and that's the key site in Chile. But there are other sites, you know, La Silla, La Serena, and there's some other sites to the south. And the reason these are important is because of their length. And you might say to yourself, well, if you already have ALMA, why move only a few hundred kilometers or 1,000 kilometers to the south? And the answer is that even these modest size baselines, these modest size differences in position, give you the increased sensitivity to the very faint jet structure that's very close to the black hole. So right now we see the black hole, but we do not see this jet structure that is launched on large scales to 1,000 light years. To do that, we need to get much better surface brightness sensitivity. We have to be sensitive to very faint emission, and these shorter baselines will help us. So I think that the new sites in Chile will be the key to understanding how energy is extracted from black holes.
Perfect. Rohan has a question.
Hi, that was a wonderful talk. So I have a two-part question. One is from audience, Clark Ramsey. So he is asking, can OREAL, the ETH, be used to investigate the other theories such as the lambda CDM and muon gravitation models? And my question was, I've always been interested in learning about the frame dragon effect and how, if future ETH missions will able to visualize it, since it'll help us understand how these black holes get so supermassive in the first place.
Yeah, it's a good question. So my understanding of the lambda CDM and the MON models are that they deal with much larger size scales. I mean, these are cosmological theories. That lambda CDM does require the GR is correct too, but they're looking at much longer time scales, much larger spatial scales. And we're looking at something that is much higher gravitational field. So I don't think we'll be able to tell the difference between those theories. This is not the proving ground for that. The second part of your question was frame dragging. So there, I think there's some really good prospects. So as going back to Vladimir's question about polarization, the parallel transport, or keeping the direction of the E field as it moves around the black hole, is something that we can be sensitive to. And as something goes around and is frame dragged, you can start to test that frame dragging using these kind of polarization measurements. We may even be able to do that with some Doppler measurements as well, or the shape of the shadow. So visualizing the frame dragging is something that we may be able to do when we start looking at dynamics of the matter around the black hole.
Great. I see Neil is back. Neil.
Yeah, I had a couple of questions from the audience. Most have been answered. I took the liberty of answering many of them, at the basic level, because some were not extremely related, and I knew you wouldn't have the time to answer all of them. And then I kept a list here, but most have been run through. Space telescopes, Julian Onions asked about space telescopes in L2. You've answered that. Sagittarius star was what everyone wanted to know about. Veronica Vasquez, Gabriela Conde Saavedra, Paulo Garcia, Diego Mardones. And most recently, the Clark Ramsey question about lambda, CDM, and MON. But then I'd like to combine it with another question, which came from Alto Robledo Oros, about stellar mass black holes colliding with Sagittarius star and M87 and connections to LIGO, to form it into a new question, the lambda, CDM, and MON, not specifically in this, but what you really emphasize is black holes. Is that all the EHT is going to do? Or are there implications? I mean, is the EHT going to work on things related to LIGO, related to collisions of collisions of black holes or black holes? Can you mention if there is some relevance of the EHT for someone who's just not interested in black holes?
Oh, well, the answer is no. They should do something else. Look, we can't be all singing, all dancing. I mean, it's like we serve hamburgers here, we don't serve pizza here. That's just what we do. But to be serious, so black holes are kind of the central meeting point of the universe. I mean, there's that one joke. This French police lieutenant has to find a criminal, and he goes to this cafe in Paris. And his boss says, "Why do you go every day to that cafe to Paris?" He's like, "Because sooner or later, everybody comes to this cafe, right?" So he knows he's going to catch his man if he goes to this cafe. And in the same way, black holes wind up being at the center of everything. So let's take your example of stellar mass objects, a star. We just heard a talk. In fact, even today, we heard a talk by Jean-Pierre Luminet himself at the Next Generation EHT conference, which I just came from, on tidal disruption events and whether we could see stars being eaten by supermassive black holes and whether the EHT would be sensitive to those. And he gave a remarkable talk about how this could be possible. For M87, it's such a big black hole that it would never tidally disrupt a star. A star would simply go through the event horizon and we would not see it be disrupted. But for Sagittarius A star, the curvature is enough that a star could be tidally disrupted, ripped apart, and we could see a very pronounced electromagnetic spectrum response from that. So in that way, you will know a black hole by its effect on what's surrounding it. And we could learn about the population of stars around black holes. We could learn about the space-time around the black hole, but also the composition of the star and the processes that we see other places in the universe by studying a tidal disruption event around the supermassive black hole in our own Milky Way galaxy. So that's one example where you can get merger events that the EHT could be sensitive to. Now but that particular merger would not have an appreciable gravitational wave signature, but it would be a merger nonetheless.
Super interesting. Okay, let's go to Julio next.
Thanks, Thomas, and thanks, Shep, for the wonderful talk. I guess I like the way you ended, by talking about the skeptical public or public that is, not particularly convinced about the work that scientists do, and I think that's quite important. I guess I was wondering, on that vein, and trying to be a little bit devil's advocate here, without the strong prejudice that there is a supermassive black hole in the location that you've made the image. So if you only had access to the image you've made, which is wonderful, is there a standalone evidence from that image that there is a black hole, that you actually are seeing a shadow of, or they're just seeing, clearly an accretion disk that is perhaps, relativistic and boosted in some way? What is that, without, arguing about the jets and all the other things that we know exist? So I guess I'm trying to see, on its own, is this enough proof, or do we need all the other ancillary evidence to convince ourselves that we're seeing the image of a black hole?
Yeah, I think it's very, very clear. So we are always guarded. We are always guided by some priors. So for example, with these general relativistic magnetohydrodynamic simulations, people have worked for decades trying to put in all of the different microphysics. And we've gone from, we now have PIC simulations, which can do even better, and they do wind up explaining a lot of what we see. And so when we look at M87 and we see this ring and we don't see it in, let's say, 3C279, that we know we're locking on to this feature, and we see that the GRMHG simulations predict exactly what we wind up seeing, that is it's a prior, but it's a very powerful prior. Now, do we know exactly what we're seeing? I don't think that we could ever say for sure this is exactly what we're seeing. But in the same way that the Andrea Ghez and Reinhard Genzel's work that show the mass interior to the stars, it doesn't actually say there's a black hole in there. It just says that within the central orbit of the S2 star, there are 4 million solar masses. And then we say, well, what else could it be? I'm not sure, is that a stronger argument than the M87 argument? I don't know. But we do have to rely somehow on the theory to guide us. Another way of thinking about it is, we've looked at this. I know Ramesh Narayan has written some papers on this, and he looked at many different modes of accretion, with accretion disks, with jet. So we've tried to look at this in a number of different ways, and the shadow feature seems to be robust. In other words, it doesn't. If you're asking, are we actually looking at an accretion disk, like an optically thick accretion disk? I think that's not possible just from the energetics. But certainly, any way you light up the space-time, you always get this feature. It's very robust.
Okay, thank you.
Yeah,
if you actually looked at another black hole and it didn't have a hole in the center, what would your conclusion be? Maybe there's another more facetious way of asking a similar question.
Yeah. Well, if all the priors for that black hole also pointed to the fact that we should see it, then I think we'd be in trouble. So and also I would want to see M87 in the future, and I would also want to see Sagittarius star. So, but I think that from what we've seen so far, it's as good a evidence for a supermassive black hole as anything I've ever seen.
Thank you.
I think that would be wonderful if you would not see a ring, right? We don't understand something. That's like an open road to discovery. That would be phenomenal. I see that Vladimir has also another question here.
Yeah, I would like a little bit elaborate about this robustness of the dark central part of the image. Do you conclude from that you actually exclude the possibility of naked singularity being there? I mean, we exclude them based on the conjecture, censorship, or the general view, but if they would exist, probably some light would be coming from smaller region than the radius of the black hole, the Schwarzschild radius. But since you see dark region, do you also claim that it can't be naked singularity or something like that?
Yeah, this is a good question along the lines that Julio was saying. There are some exotic objects like naked singularities, gravistars, boson stars. We call them black hole mimics, which are not quite black holes, but have many of the same similarities. They can, make shadows and so forth. For the naked singularity solutions that I know of, the shadow for the mass of this black hole would be quite a bit smaller. And so the fact that we've seen it at the size that we do is evidence, to my mind, that it's not a naked singularity. There are some objects that are harder to rule out. So a boson star, for example, which can be just a little bit larger than a black hole, is difficult to rule out. There you have to appeal to the fact that it's hard to think about how a boson star would launch a jet. So you need also to understand the fact that, well, M87 has this 10,000 light year jet, and how do you launch that with these exotic objects? So, and those are harder to do. So there will always be some exotic objects that are almost impossible to see how you would make that could mimic a black hole. I mean, it's like, how to describe it? Like you walk down the street and you see this gray thing up in a tree. Well, it could be a piece of plastic that was blown up there, or it could be an elephant. But you don't immediately say, well, that's an elephant. It's more likely something explainable that is easy to do. And it's easy to see how you might make a black hole, much harder to see how you'd make a naked singularity or a boson star.
On the other hand, there used to be times when people thought black holes are very exotic. You mentioned that. So.
Yeah, very true, very true. Well, so I will say we remain skeptical. I mean, we want to go back and observe this again. We want to observe Sagittarius star. What we're very excited about is if we can make our measurements this year, we'll have 3 new dishes. So we'll have a much better array than we had in 2017. And so we'll get much higher imaging fidelity. So that would be another angle at which to study this.
Okay, John has a last question.
Yes, last question. So this one more from me. In addition to M87, there are, I don't know, half a dozen other galaxies in Virgo that have similar stellar masses or even more, like M49, but they're not AGN. Does it need to be an AGN and have this active accretion in order to see that? And if not, I mean, if just this kind of sea of stars in the background is enough, that may address some of the other questions about whether you're seeing effects in an accretion disk. And so could you use this on something like M49 of roughly similar stellar mass that may have a similar size black hole, but no AGN? And if so, have you thought about that?
Yeah, so we've considered that, but the difficulty is you really have to have a radio loud AGN. So you need to have something with a brightness temperature, and therefore a very, very small bright center that you can detect with this technique. Put another way, anything that's illuminated with stars would be thermal, and the VLBI technique can only look at things with a brightness temperature of at least 10 to the 8th or 10 to the 9th. So it would be, you couldn't see something that was illuminated by stars. It has to be synchrotron radiation or something else coming from very close to the event horizon.
Thanks.
Okay, so thank you. Let's wrap this up here. let's let Shep go to his deserved rest after a long week. Thank you so much, Shep, for your time. Thank you for the presentation. It was a beautiful overview, and all the best of luck for the future with this project. I'm sure there will be fantastic results coming up very soon. So we're looking forward to this.
And thank you. It's been a real pleasure.
Thank you. Thank you for the audience for being here and asking great questions. And thank you to the panelists for also joining us today and your time. Please, everyone, be so kind and fill out the survey after this webinar. And I just would like to announce briefly the next webinar in the Golden Webinar series, which will be given on March 5th by Aline Tolstoy, and she will be talking about fossils of galaxy formation, faint dwarf galaxies around the Milky Way. So everyone, please stay safe, stay healthy, and until the next Golden Webinar in Astrophysics next week, take care. Bye-bye.
Bye.
Bye-bye.